Josh, question?
Yeah, homework's due on Sunday, midnight.
Homework is due Sunday, the end of spring break.
Oh, good.
And the quiz, post-quiz, I think it opens Saturday morning of that weekend and it closes Monday night. Alright? There will be a post-quiz, there will be a pre-quiz for Monday. Anything on Monday is fair game for the exam. That's the way I do it. We don't really have time this semester to pause, reflect, do a lot of that. That's what our supplemental instruction is kind of meant to do in office hours. So we will have ice tables on the exam, which is something we'll touch on tonight. Alright, go ahead and answer this question, click in your answer, and we'll talk through this, and then we'll get to the quizzes. Let me know if something comes up. All right, we have 36 responses. All right. Can someone volunteer? Let me do one thing actually, and then see how you guys feel about this. So in order to calculate an equilibrium constant, first we're always going to write it out. What's on the top? Concentration of the products at equilibrium. So concentration of NH3 over concentration of reactants, right? All right, and then we just plug in the values and we find the number, right? Why is that wrong, Danielle? Why is it wrong?
They're not all the same.
Right.
The nitrogen is in.
The nitrogen is what? Okay, so we have millimolar, we have molar, but I expect you guys to be pretty comfortable converting those from like 805 millimolar is 0.805 molar. So what is totally wrong about what I wrote here? What am I missing? Matt?
You didn't balance the equation.
Oops.
That's gonna put exponents.
Okay, so go ahead and balance that equation. Always use a balanced equation. Figure out how that influences your K. All right, so 1 more minute to balance and put in your answer now.
Let me know when you guys get your final answer.
All right, so as you guys are typing in those numbers, can someone tell me what I need to do to modify my Kc expression here? If anyone's done. Ruby?
You have to square the value for the concentration of H3 and Q the H2.
Okay, so our balanced equation is 3 hydrogen molecules plus 1 nitrogen molecule yields 2 ammonia molecules. So that means that we have a concentration of NH3 squared, concentration of hydrogen is cubed. Does that change your value? Yes. Yes. All right, so we've got a balanced equation. We have our equilibrium constant. I had a really good question a couple minutes ago. Are there units on our equilibrium constant? No. It's one of the very few times where you don't put units on it, and there's a whole bunch of explanations for why, and none of them make sense, so just accept it. It sucks. But can you use moles instead of molarity in equilibrium constant? Absolutely not.
Because of concentration.
So the concentration is really important that you take volume into consideration. So if you're ever just given the moles, you have to do molarity whenever there's an equilibrium constant K. You cannot just use moles. And that's because if you think about the number of moles versus the number of moles per liter, you're going to square that, and that's going to have a big influence. So the stoichiometric coefficients play a role. And if you want to try one time, try doing it with just moles, and then do the same calculations with molarity, and you'll see that they're not the same equilibrium constant. All right? So we have all our values. We plug them in. We make sure to go from millimolar. We use appropriate units for that. And let's see if you guys are all on the same page here. I got 0.36. Looks like that's the majority answer. A third of people got that. But how did you guys get something different? So order of operations is going to be important here. So make sure to go back and check your calculations to make sure that 0.36 is the value you get.
Make sure you're using the right concentration.
One of the things that's very likely that people could do wrong is if you do 0.75 squared divided by 1.25 cubed times 0.805, that's going to basically put this back up on top. So you need to use parentheses, order of operations. Don't forget order of operations. All right. So then I want to know if we look at the reverse reaction. I'm going to give you guys 45 seconds to answer this question. Same exact reaction, same equilibrium concentrations. What is the reverse reaction to equilibrium constant? So I just flipped the two sides. So our products are not considered reactants, or reactants are considered products. Probably don't even need 45 seconds. All right, we're almost at 45. How can we save ourselves a lot of time on this calculation? Do we have to plug everything back in and do the same calculation? Is it basically this, but we flip the top and the bottom of products and reactants? That's not the fastest way though, right? Moab, how do we do it faster than that?
1 over the previous value, or 1 over 0.36?
Done. 1 over 0.36 will give us what value? 2.8. That sounds reasonable to me. Because if we go back to the previous page, the inverse of these is going to be the inverse of this value. You can prove that to yourself if you'd like. All right, so then let's take a look at this particular setup. And I want you to tell me if this reaction is at equilibrium. Yes. No. We need more information. This is question number 3.
cataracts? Actually, white.
Yeah, something like
Moab? Alright, we have a lot to get through today, so please help me out, and let's try to keep as focused as we can. How do we answer this question? We have a mix. We have a 2-to-1 response, so that tells me we're not sure how to answer this. Process-wise, what are we doing? Leah?
We don't have a KC. We also don't know.
Do we have a KC? Do we have a
Are we
KC?
using the same? Which one are we using?
It's the exact same reaction.
Which direction is it?
Doesn't matter. As long as you keep it the same way and define it the same way, you can use either one of them. So this reaction right here, does this lie to the right, to the left, or does it lie in the middle? It is a tiny bit less than 1, but for our purposes, if we're talking about lies to the left or lies to the right, we're typically going to have 100, 1,000, or more than that. This is 1/3, so this is pretty close to lying in the middle. So this is almost an equal mixture, right? Because these concentrations are all almost the same. Right? They're all about 1 molar, and then you have the exponents to kind of tweak it a little bit, but I'd say this reaction lies in the middle. The other one, if you flip it over, it's 2.8. So then it lies a little bit to the right if you're looking at the reaction that way, but pretty much in the middle as well. So,
Sorry, what values of that are close to the middle?
so you'll see some equilibrium constants that are 10 to the 40th and 10 to the negative 15th. So that's like a billion versus 3. So these numbers are fairly close to the middle. So once you have like a number of 100 maybe or bigger, you'll get used to it once we do more calculations like this. Yeah.
So if we were to put it to the left because it was less than 1, would you mark it wrong? Because that's how all Al does it.
I would want you to say it's almost the middle, slightly left to be okay.
Okay.
But the question is, we look here, are there more reactants or products? Well, this is a product. These are reactants. So there's not too much of a difference in their concentration, right? All right, so either one you use is fine. So if we know we have equilibrium constants for both the forward and the reverse reaction, how do we tell whether this is at equilibrium or not? Christina?
I said that it wasn't at equilibrium because you have parentheses around.
Okay, so very good observation. There are not square brackets, but that only means I'm not saying it is at equilibrium, but parentheses can be any concentration, including equilibrium. That was one of the things, I guess, at the last activity. They had parentheses can be, when it is at equilibrium, parentheses can also be shown as square brackets. Love?
I solved for K using those concentrations.
Okay, did you do the forward or with ammonia on the right side or ammonia on the left side?
Going to the right side.
Okay, so you know that our K is equal to concentration of NH3 squared over the concentration of H2 cubed times the concentration of N2. Okay, and then we put in these values. So what do we find? If we go ahead and put in 0.531 squared over 0.0345 cubed times 0.00280. So what do we get numerically?
It's like 2.5 million.
Yeah, 2.5.
10 to the 6th? What does that mean? Say again?
Said I was right when you walked by? Sorry, I kept getting that number. I'm like,
I thought you meant for the equilibrium constant you got that number.
Yeah.
Okay. So this number, how does that compare to our K?
way different.
So 0.36, that was our equilibrium constant for that direction, right? And we can say that those are not equal. So that tells us that unless the ratio between these, with their stoichiometric coefficients as exponents, are equal to K, that it is not equilibrium. So I'm going to give you guys a new term. The new term for this is not Q, or not K, it is Q. So that means that we use, it's called the reaction quotient. It's not complicated. It basically says that we try to calculate K, but if it doesn't actually, if it's not at equilibrium, if we don't know it's at equilibrium, we can't call it our equilibrium constant. So we know that our Q is this number. If this Q were equal to K, what could we say about the reaction? It's at equilibrium. If it's not, then we know that the reaction is not yet at equilibrium because it doesn't have the same ratio as we know we have when we have our equilibrium. All right, we're going to spend some more time in class on that today, but for right now we're going to do a quiz, so go ahead and put your calculators, everything on the ground. This is brain only. No calculators, no anything, so go ahead and sit on the chair next to you on the ground. Keep your quizzes face down until everyone has them, and then you guys will have about 5 minutes. It shouldn't take long. It's not
Too bad. I guess I just have to leave.
Does anyone not have a quiz? Does anyone not have a quiz? Corbin, you good?
Oh, yeah.
Okay, so remember that you're not allowed to use a calculator. Circle all answers that are right. This isn't a B, or all of the above kind of thing. It just is based off of those 2 videos. That's it. Just want to know if you can look at an exponent and utilize them. Go ahead. I think I'll give you guys about 5 minutes. Make sure your name's on it, and then we'll collect them in the end of 5 minutes. This is on your own, without a calculator, without a phone.
No phone.
All right, our learning outcomes for today are determine if a reaction is at equilibrium or not. You guys already did that. That's just looking at calculating K, but it's not really K if it's not at equilibrium, and comparing that to a value of K. And then we're going to predict which direction the reaction will proceed in order to reach equilibrium if it's not already there. And in order to help us do that, we're going to use a Rice table, which you guys will see at the end of this class. So let's take a look at this graph, and I want you thinking about 2 ways to answer this question. At time 0, is this reaction at equilibrium? At time 0. Go ahead and click in your response and then check with your neighbor.
It's definitely true. That's so good. Because that's the last thing. This was right.
Talk to your neighbor about 2 ways you can tell you seem to be in agreement. I want to know how you decided that. All right, can I hear from some people who are normally a little quieter? Is this reaction at equilibrium, yes or no, at time equals 0? And then how do we know? Maggie, would you like to share your answer? Okay, no, it's not at equilibrium. Why? Give me one way that you figured it out. The second one's a harder one. Maggie, you want to pass, or you want to? All right, Logan.
All right, 1 is not in the equilibrium phase, and 2, everything is still moving. So like you don't have anything that's like staying at the same rate over time. Like it's all like you got this giant concentration which is at 4 molal, then 3, and then all the way at 0. So there's no way that this.
Okay, so you touched on a lot of different things, and we're going to be even more specific on those. So you mentioned rate. What does rate have to do with us making that conclusion that we're not at equilibrium at time equals 0? I have someone else. Bria?
When you reach equilibrium, usually the rate kind of like equals out on all of the like products and reactants.
So how do we know that? What do we see in a graph that tells us that the rates are equal?
The line will be all straight, and then that just means that the coefficients would have to be like making it equal, right?
So careful on the coefficients part. That's going to be a little outside of what that particular description was. So if we see these lines are flat, what does it look like the rate of conversion of A and B to C is? What does it appear that the rate of conversion of A, or consumption of A is? Looks like it's 0. Is it actually 0?
No.
No. What is it? The net change is 0 of concentration of C. So C is being consumed at the same rate as being produced. All right, so hopefully you had that as a takeaway from activities 37 and 38 that we worked on. So the lines are not flat. You can see that the concentrations are still changing at time equals 0. Great. What's another way? We just talked about it. Ruby.
You can use the formula for Q reaction quotient, and use the numbers for molarity that they give you at time 0.
All right, so I want you guys to find K for this reaction, and then we're going to do what Ruby said. We're going to compare Q at time 0 to K. So go ahead and calculate our equilibrium constant for this reaction.
So you want KC?
Yes. They're the same.
Did you do all the same things? Did you do all the same things? Then you want some things. They're supposed to be what, like 4? No, it's 5. No, it's 4 because the 0 point. Yeah.
So I did it right.
Not actually.
All right, the volume went up, so we're done.
We're just more excited about getting
Figure it out, man.
that's what it is. God bless.
That's how you say things. Just ish.
All right, so how do we find our equilibrium constant for this reaction? Can I hear from a new voice? Chelsea, do you want to share? Lauren? What about the products? Be more specific. I can't hear you. There we go. So K of our equilibrium is concentration at equilibrium, right? This is always going to be defined as square brackets if it's K. If we don't know, we need to use parentheses. But now we know it's at equilibrium because the concentration is stabilized. Over the concentration of B times the concentration of A, whatever way you want to write that, is fine. And so we have those numbers here. What are the stoichiometric coefficients we're raising those concentrations to? 1, all around. So we multiply those two numbers on the bottom, divide C by that, and what do you find for your value, Josh?
3.005887. I mean, 6 feet is a lot.
And so our limiting sig fig is which one? B, 4 sig figs. So we
I
would.
didn't understand. So in the real world, when we don't have a complete unit, I guess at the end, you just record the whole data.
So someone measured this concentration, and this concentration.
That part. But when we get a final value without units at the end, it's just a value, right? We know this is 3.005887. That's given.
Right.
So why do we cut that off?
But according to the calculations, we have less certainty here than we do for either of these two.
Okay.
So that means that our answer has to be limited to the least certain value that we have. We can't make up certainty that existed. We can't say, well, I know that this was a couple past here. We don't know what that was. So we're not imparting additional knowledge on something that didn't exist. So then how do we use that to do what Ruby said and determine at specific time points if we are at equilibrium or not?
Put in the concentrations and see if they're equilibrium.
So we do the same thing, but we call it Q instead. And then we do the concentrations in parentheses, and we look at what is that ratio. Is that ratio 3.006 or not? Kayla? Oh, your hand just happened to be up. So what's the concentration of C at time 0?
0. So it's 0. So it's 0. It's equal to 3.
And then we have, what, 4 for A, 3 for B? Molarity? So is that number really big, really small?
0.
0. So it's really small. If you have 0 on the bottom, do you consider that number really small or really big? I know it's undefined, but think about, is it really big or really small? If the denominator is 0, it means that it's an infinitely large number. That helps us place whether it's bigger or smaller than k, because if you just say undefined, then you're like, I don't know, it's bigger or smaller. It's kind of useless. All right, so I want us thinking about how it relates to k. So if this reaction, if our Q value is 0, which direction is this reaction going to go to reach equilibrium? Is it going to go to the right or to the left? I see people pointing in opposite directions. Narina, you want to describe why you're pointing to the right? Because Q is less than K. Okay. What does that mean mathematically? Let's think about our fraction. Tripti, do you want to add to that?
Is it because if the numerator increases, then the Q would increase?
Can you say that again one more time?
So if the numerator increases the
Of Q.
it would reach to the and it would get.
So in order to get this number closer to our equilibrium constant, the top has to get bigger. What is the top in this case, a reactant or product? It's always a product. So as the product increases, it takes away some of this, and this number goes from 0 to a very small number, to a less small number, to a medium-sized number, and kind of keeps moving in that direction. So Q is, you can look at your book and it gives you a table to memorize. If Q is less than K, do this. If Q is greater than K, do this. If Q is equal to K, we're at equilibrium. I want you to forget about that. I want you to just think about, what does this fraction do? What does it need to do in order to give us a value that is close or the same as our equilibrium constant? So if we're doing a Gibbs free energy diagram for this, where does equilibrium lie? So go ahead and really quickly just draw a Gibbs free energy diagram for this reaction. Think about where the minimum lies, and then think about where Q is at time 0.
At this point, it's going to be close to A and B to the reaction.
All right, so let's see your thumbs pointing to the left, to the right, or in the middle. So where is the minimum going to lie for this graph? Is it going to be slightly that side of the middle, slightly that side, or point straight up if you think it's going to be pretty much in the middle? So is the minimum going to be in the middle? Is it going to be on the right side or on the left side? Come on, give me some thumbs. Show me what you're thinking. Like we were doing some little dance moves over there with everything in between. All right, so what would a K value be if it was the minimum was right in the middle? If the minimum was right in the middle, which would mean we'd have an equal mixture of reactants and products, what would this value be? It would be 1. So 1 is exactly smack dab in the middle. If it's bigger than 1, right, we're slightly bigger than 1, does that mean more products or reactants? More products, because products are always on top. So that means our minimum is going to be just a little bit right of center here. Barely right of center. Where is our initial Q value?
This is at time.
This is at equilibrium. So this shape is defined by when we reach equilibrium. And then we say, well, where is time 0? Where is that mixture on this graph? What are you saying, Humphrey? We have only reactants and products. Or sorry, only A and B, only our reactants. So this time point, this is where we have Q equal to 0. On that far left side. We don't have any products at all, right? We've moved nowhere along this energy minimum line. So if this reaction does start, and it starts moving towards products, you guys said that it's going to move to the right, and that's going to be energetically favorable. So think of the ball rolling downhill. You set the ball up here, where's it going to go? And it's going to settle at the most energetically favorable mixture of reactants and products, which at this temperature gives us this K value. Questions? So next week, we're going to start doing some calculations where we actually compare how much energy can be released by a reaction. So ATP to ADP, right? You talked about this in biology class, hydrolysis of ATP. The reason that that reaction is so favorable is because you can give off a lot of Gibbs free energy when that reaction occurs. And the more we have only one reactant, the further apart Q and K are, the more energy can be given away. Think about how far the ball rolls downhill from here versus if it were here. You can get a lot more energy the further you pull Q away from K. So that's kind of, we're going to do a little bit of that next week, and then we're going to do a lot of it later when we talk about thermodynamics in this class. How to tether two different reactions together to drive a reaction forward with a reaction that is highly favorable. You can push a reaction that isn't favorable forward as well. All right. So then let's take a look at a whole bunch of reactions. And let's first determine what our equilibrium constant is for this reaction. Let's take a look at the table. So we started with all reactant N2O4, none of the product. There's our balanced reaction. You guys go ahead and calculate our equilibrium constant K, and then we'll use that in our discussion. Go ahead and quickly calculate K. Type that in. Raise your hand if you need any help.
Are we doing
All right, 30 more seconds. Find the equilibrium constant. Click it in, please. All right, closing out. So the majority answer was, but only by 60% of the votes. So do we just divide the concentration of products by reactants? No. What are we forgetting if we do that? Our stoichiometric coefficient. So what I did here is I made a table where I'm actually showing what are those values of concentration of products divided by reactants and the concentration of the products squared over the concentration of the reactant. All right, so we started with all reactant, no products. How do you think these two numbers are going to change if we start with different amounts of reactants and products? Are both of them going to change? What trends do you guys see? Say again? Kayla would say?
the K is pretty close.
So which column is our K? And this column right here, if we forget the stoichiometric coefficients, the random numbers, right? So this is a useless column. It gives us no information. It's not about the ratio between products and reactants. So basically, if you look here, we start with only reactants in the first trial. We start with almost a lot more reactants than products in the second one. We start shifting it, and then the very last one we do all products. And what we find is that no matter where we start on this line, that reaction is always going to end up achieving our equilibrium constant. That mixture of reactants and products related to the stoichiometric coefficients is always going to end up with the same number. And we're not going to get into the law of mass action, so I want you to decide whether each of these is at equilibrium or not. How are you guys going to tell whether it's at equilibrium or not? So go ahead and click in whether this is at equilibrium or not. Yes, no, can't tell. And then the second question is going to be, what has to happen for this reaction to get to equilibrium? A couple more seconds. All right, can I have someone share what they decided and why? And I think the answer is probably pretty straightforward, judging by the responses, but I want to have a really clear definition of how we can be absolutely certain. Love?
Well, if you plug in the values to find Q, you find that Q is equal to 0, which means it's very left shifted.
So we're all the way over here. What does the diagram look like for this reaction? Is this an appropriate Gibbs free energy diagram for this reaction? Where does the minimum lie for this reaction? Talk to your neighbor. Where does the minimum lie? To the left, to the right, in the middle? All right, go ahead and point. Does the minimum lie to the left, to the right, or is it in the middle? This is the reaction that we just had on this page. What is our equilibrium constant for this? 4.66 times 10 to the negative third. Does that lie to the left, to the right, or in the middle? It's less than 1. So maybe the minimum is over there. One way to think about that, right, is if you have 4.66 times 10 to the negative third is our equilibrium constant. We're thinking about the ratio of products over reactants. You can say 1 over 4.66 times 10 to the third. So for every one product, there's 4,660 reactants. Avery?
So just for clarification, the middle, if we're to look at the Gibbs, what that is, it's supposed to be equal to 1. That would be like, if it's equal to 1, that would be a middle.
If we have a k value of 1, or we're really close to it, then that sits in the middle. So this one is much smaller, which means that the denominator is smaller, bigger, products over reactants. Smaller value, denominator is bigger, sorry, math. So it means that we lie to the left. But the question that I just gave you guys was this one. So if we do what Love said, and we look at our Q value is right here, 0. It's right up against the far left side. So then, in order for that reaction to reach equilibrium, let's go ahead and answer the second question here. So given time, this reaction will generate more reactants, products, or it's going to stay where it is. Go ahead and click on your response for these concentrations. All right, it's a 2-to-1 split. Talk to your neighbor. Try to decide what you're going to generate more of as the reaction proceeds.
Nice chart. I went through and did K values. Pretty close.
Q values. So then you compare it back to K and say if it's the same. Yeah. Q and K, yes. All right. Can I hear from someone who had a discussion, and maybe decided it goes one direction or the other, and which way that is? Savannah, you want to share your group's discussion?
We said, I don't really know how to say it, I just thought it was products. I don't
Okay,
know
why?
how to explain it. Because if there's none, I don't know, it made sense.
You're on the right track. Josh, you want to add?
If there's none, you gotta make them. Get there.
Okay, so we know at equilibrium we have a mixture of both. This number is not 0 or infinity, so there has to be some in both. We start, and there's none of one of them. The other way to say that is, you can't make any N2O4 without NO2. So we can't make more reactants. Right? It's impossible. If you look over here, how can we describe that same thing? Drifting? So the reaction, in order to proceed towards the minimum, you're going to progress to the right. Going to the right in any reaction means generating products or consuming reactants. So a number of different ways that you can describe that. All right, let's go through the rest of these. Second one on your table. What do you guys think about this one? Go ahead and click in your response. Is it at equilibrium? Yes or no? Another 15 or 20 seconds. Is it approximately the same? All right, we have a 2-to-1 answer again. So how do we go about this? What is the process? Danielle? We find Q. So what did you find for Q? Great. I don't know about 4.66, 4.67. So our K value is 4.63. Is that at equilibrium? Pretty darn close. Experimentally, you're not going to find a value closer than that. Okay? If we're thinking about on this giant scale here, that's the same. So I absolutely think that those are equal. We can say that this reaction is at equilibrium. So then what does that mean about the second question? Given more time, what's going to happen? Click in your answer, 15 seconds. For this mixture, what's going to happen if you give it more time? What? Did I answer your question?
Well, I mean, I was just.
Your argument, because I was talking about a different question. Wouldn't you like get a little just tiny here?
I mean, it's always going back and forth, so it's going to be constantly fluctuating.
But it would be enough like the
Closing out. We're at equilibrium. We're constantly making more products. The products are being used up at the same rate. It's a constant ebb and flow, right? A dynamic equilibrium. And so there will be no net change. We're basically at equilibrium. You can't get much closer than this to a value that you found. All right, what about this one? Go ahead and 15 seconds. Is this equilibrium, yes or no? And closing out. So I can't remember what the answers are. So the answer most people said is no, it's not at equilibrium. How do we know? Careful, we're not saying the reactants are the same as products. What is it that we're looking for, Logan? Our Q is infinity right now. So where is that on this diagram? Over here. We're all the way on the far right side. We know that at equilibrium we don't have an equal mixture because that would be a K equal to 1. We know that we have more reactants than products, but we're nowhere near that. The other way to say this is that because our K is non-zero, it means that we have a mixture of reactants and products. Once again, we don't have one of the two. All right, so then in order for this reaction to reach equilibrium, what are we going to do to reach equilibrium? So we're answering this question now for this last reaction. We're going to generate more reactants, more products. 15 seconds. Closing out. All right, so why are we going to generate more reactants? Can I hear from a new group? Kayla. So we're not at an energetically favorable position right now. We're way over here. In order to get Q closer to K, we're going to generate more reactants. Go left in the reaction. Fantastic. What's another way to say that? Another thing we can say.
Our Q is larger than our K.
Q is larger than our K. We also have no reactants. We know at equilibrium we have both. So all those are fine ways of thinking about it. All right, what about this? I think this is our last one. There's one more past this. And if you finish this calculation, calculate the last one as well. Do a couple more seconds. Closing out. We're not sure on this one. Why? What's going on? Q value we found, I got 4.63 times 10 to the negative third. Is that what you guys got? So is that at equilibrium? So are we going to generate more reactants or products or neither? We're here. We're right at that minimum. We're the most stable mixture of reactants and products. All right, last one. 10 seconds. Don't calculate. Couple more seconds. And closing out. What's the misconception I'm trying to pull out with this question? Logan?
That both of the concentrations are equal, so we would say it's at equilibrium.
Fantastic. That's a misconception that we don't want to hold on to. Unless the K value is what? If the K is 1, then this is at equilibrium. Well, it depends on stoichiometric coefficients. But this would be very close. So the Q value on this one is probably going to be pretty close to 1. What did you guys find the Q value to be? Did anyone do that yet? It is 0.065. Alright? And so that is not at equilibrium. Alright, let's do one very quick question here, and then we're going to jump to the last page. So here is a diagram that is red and blue, just like you guys have on your paper. Alright, go ahead and decide if this reaction is at equilibrium, or if it needs to proceed to the left or to the right from where you see it right now. You have all the information you need. And just in case, I probably should have done these in other colors. Are red and blue for colorblind? Can you see those? Do you know?
It's red and green.
These two are red. The rest of them are blue. Just come on. All right, closing out. I want to hear the process. All right, can I hear someone share the process? Someone we haven't heard from yet. We've heard from a lot of voices, and I appreciate that. Can I hear from David, Marlene, Felicia, one of you guys? How would we answer this question? Okay, for this diagram, or? Well, so we need to do a calculation first, I think is what you're getting at. What do you calculate? What are you doing products over reactants? How do you find K?
Well, don't you do well, actually you can do Q, right?
Which one?
I guess either.
Alright, so can we add specificity to that? So we need to do both. So how do we get there? We have the equilibrium concentrations that we use to find K. So what do you find for that? What is the value? I think it's a half, right? Alright, so if K is a half, does that mean at equilibrium we have more products or reactants? Did I do that right, by the way? You guys are quiet. Okay. Oh, it's not exactly, so it'd be 2.8, right? So what did we find for the value? It's about 0.4. So do we have more products or reactants at equilibrium? The bottom of the denominator is bigger, so that means we have more reactants. Is that what's shown down here? So then does the reaction proceed to the left, to the right, or is it stable? So we know that at equilibrium we have more reactants than products. Is that true down here? So here we have more products. So our Q value that we would calculate would be and we'd have to do concentration if we really wanted an accurate value. So this would be, we could say they're in 1 liter, they're in the same volume. Don't worry about that for right now. All right, so the ratio is not what it needs to be. So in order for this reaction to reach equilibrium, we would need to take products and generate reactants.
More reactants. More red. Is red products or is blue products? Okay.
All right, so then the last thing that we're going to do for class today, because I'm trying to make sure that we get as much preparation as we can. There's a few other options like that you guys can take a look at, but all right, so go ahead and on the last page, we have a little problem. Let's take a look at this reaction and think about what's going to happen to this reaction based off of where we are. So process-wise, can someone share what steps they're doing?
I'm converting
Converting what?
moles to divided by milliliters.
So you're finding the molarity. Really important. If you just start plugging in moles, let's not do that. So we need to find the molarity. Once we find molarity, what do we do with that? Are these the concentrations you guys found? We have 4 molar, 8 molar, and 8 molar, and 4 molar. What do we do once we have the concentrations? And did I use the right symbols there? These should be non-square brackets. These should be parentheses, right? Because we don't know if it's at equilibrium. What do we do once we have the concentrations? Let's go ahead and find Q.
But didn't it already give us the KC at that temperature, which is technically Q?
No.
Why not?
KC is at equilibrium. Q.
Yeah, but why does it say at this temperature?
So it's the same exact setup, but we're using the concentrations that we have exactly at this point in time. They may give us the same ratio as K. If they do, what does that tell us? We're at equilibrium. So if I plug those numbers into my Q relationship, I found Q is 64. What does that tell us? Are we at equilibrium? We are not at a place where Q equals K. So then what's going to happen? We're going to shift products to reactants? Or are we going to shift reactants to products? What's going to happen? This number is bigger than what we're going to get for what we need for a K. So what has to happen to this fraction in order for it to get closer to K? We need a larger denominator and a smaller numerator. So that means what is on top is going to go away. What is that? Products are going to go away. Reactants are going to be formed. So let's keep that in mind. In order for this reaction to reach equilibrium, we have to consume products to generate reactants. If we know that at equilibrium we end up with 5.56 molar of methane, how does that help us figure out what the final concentrations of all these things get to at equilibrium? So this is where a rice table comes in. What is our initial concentration? What changes and what is equilibrium concentration? Have you guys seen one of these before? All right. So I know that I'm over time. This will help drastically in your homework. Do we know our initial concentrations of all of these things? We calculated that, right? Do we know the final concentration, the equilibrium concentration of any of these?
One of them.
Just this one, right?
Then we gotta do that 2x.
2x.
So, for every one methane that goes... wait, are we going to the left or to the right from where we started? That means that we're generating more of these guys, and we're taking away from this side. For every one CS2 that goes away, how many H2S's are we forming? One goes away, we make 2. 4 hydrogen go away for every 2 H2S that we're making. So then what is our value here at the end? We're taking 4, we add x to it, so what is that? 4 plus x. We know what that value is. 8 plus 2x. Do we know what that value is? We can find it though, right? We take some away from the 4 molar concentration and the 8 molar concentration. So this is called an ice table. It allows us to figure out how much reactants are being used, products are being formed. But if you don't compare Q to K first, then you might as well just forget it because you're not going to know your signs. Alright, so you will have a chance to practice this. That is what activity 40 is, so please give it a try if you get a chance. Hope to see you guys over the next week.